This is Computer Science 305, Programming Languages. This is ML3 Part 4, and we're talking about predefined higher order functions. So far we've talked about more pattern matching constructs, like for example we looked at the case statements, which we saw was a generalization of if. We also looked at anonymous functions and how we can actually use those to create functions, and then finally we looked at how we can build up higher order functions through currying, as well as just higher order functions in general. And finally now we're going to be looking at predefined higher order functions. And so there are three, I would call these three important higher order functions in most languages, functional languages. We have map, FoldR, and FoldL, right? So actually FoldR and FoldL are very similar, as you might guess from the names, right? It's fold right, fold left. And so basically the map function is basically used to apply a function to every element of a list, and then you collect a list of results. So essentially, right, we take some operation. For example, in the example there, we have the negation operation. So if we open up the standard ML or polyml, we can then say map and then the negation operation, and then we have a list 1, 2, 3, 4, right, and then it returns the negation of every single item in the list. This is a very powerful function. This is part of actually the basis for an even more important technique in the rest of computer science, in distributed systems particularly, and machine learning, which is called MapReduce. It's also used for data science. So MapReduce is we basically we have a bunch of data, and we have some function, right? In this case, it was the negation, and our data was a simple list. What we want to do is we're going to effectively apply the operator to the list, and then create an output list, right? A result. And so that's mapping each item in the original list to the result of the resulting list through that function, right? So that's what it does. It's creating a map. Like we can think back to discrete mathematics and the definition of a function, which is a mapping from the domain to the range, right? That's what this is doing. And the operator that does that mapping is whatever operator we supply. Now this could be a function that is quite intricate and complex, or it could be as simple as negating each item. Now the interesting thing, there's a second one which is called reduce, but we're not going to get into that right this instance. We will get into it a little bit later. So as I said, we could use this map function to apply a function to every element of a list and collect the lists of results. So we also could say, using an anonymous function, we could say map fn x plus 1 to a list, right? And 1, 2, 3, 4 again. And lo and behold, we get 2, 3, 4, 5. We could get more and more tricky, right? We could say map fn of x, where we say mod x mod 2 equals 0, right? So then this is this is a question, right? So x mod 2 equals 0. So now we're checking if the mod of x by 2 is equal to 0. So this will return obviously a true false value. So 2, 3, 4. And if we do that, all of a sudden we get, on all of the even ones, we get a true, and all the odd ones we get a false, right? As expected. Now finally, if we say map, we're going to use the op keyword again, op plus, and we're going to apply it to tuples, right? A list of tuples, of two tuples actually, a pair, 3, 4, and 5, 6. Now this should return a list of results of those additions, right? So the first one would be 3, then 7, then 11. And lo and behold, that's what we get. Because if we recall, if we look at what op plus tells us, is that it takes in a tuple of ints and returns a single int, right? So if we understand what the functions take in and what they return, we then get, for each item in the list, the return value. So that's the mapping of the function, right? Yay! We figured it out. Okay, so the map function is curried, right? So if we would just look at what map is, map by itself, right? It is a curried function that takes in some unknown A and some unknown B function that does that, right? So that's the first argument, is a function. The second argument is a list of unknown A, and then the return value is a list of unknown B. So again, if we create a val f and we set it equal to the map on op plus, right? And then we apply that to a list of pairs 1, 2, and 3, 4. We get 3 and 7 as our result, right? As expected. So the map is a curried function, and now we can use this to do all sorts of really cool things. And this is like becomes the basis for a significant amount of current work being done in computer science. For example, if you think about if we can use this, and it's I will talk about the reduce part. Reduce is basically just where we take all the value returned from a map, right, the list value, and we are going to compress all the through some other function, right? We're going to use another function which will aggregate all those values down into a single value, and then we can actually put that into another list, and we create these MapReduce pipelines that allow us to essentially do all sorts of high-level computation across multiple distributed data nodes, and allows us to do all sorts of distributed computing that gives us capabilities that you can do on things that you can do on like Amazon Web Services, Google App Engine, etc. To do very high performance computing when we're looking at large amounts of data. Anyway, moving forward, so we saw that the map function is curried. So the FoldOut function, right, is essentially a reduce. It's used to combine all the elements of a list. For example, to add up all the elements of a list, we could write folder op plus 0x, right, which takes a function f as a starting. It takes a function f as a starting value c and a starting value c and a list of x and computes, right. So this is essentially what it's doing is it's computing x sub 1 and then f on f on x sub 1 and then f on x sub 2 all the way down until we get to c, right. So fold r op plus 0 and then the list 1, 2, 3, 4 evaluates as 1 plus the contents of 2 plus the contents of 3 plus the contents of 4 plus 0, right, which is then 10, which is expected, right. It's just the summation of 1, 2, 3, 4 with 0 at the end. And that's so if we were to run this, right, we can run this simple operation, fold r op plus 0, 1, 2, 3, 4, and we get 10, right. If we use the op multiply, right, and then we did 1, right, because if we did 0 it always ended up being 0. 1, 2, 3, 4. So 1 times 2 is 2, times 3 is 6, times 4 is 24. Oh, sorry. What did I mess up? I can't tell. Unmatched closed comment. Oh, hello. Fold R. You actually have to have a space after the star, otherwise it considers it a comment. Star space 1, 1, 2, 3, 3, 4. Right. Then it gives us 24 as expected. We can also use the exponentiation, or sorry, the string concatenation operator, op concat, right, on a set of strings with the empty string as our base. Right, A, B, C, D, E, F, G, H, I. And we can also use the cons operator to construct a list, right? So fold R op cons with 5 being the base, and then we can say we have the list 1, 2, 3, 4, which then cons everything together, creating the list 1, 2, 3, 4, 5, which is very nice. So we also should note that, of course, the fold_r function is a curried function. If we want to look at that, we can say fold_r by itself, and it tells us what it takes in. It takes in a tuple of AB mapped to a function mapping the tuple AB to B, right? And uses that entirety to that function to map to B, which then maps to a list of A, which is then mapped to a B finally. So good times. If we were then to say fold_r, right, and then we give it the actual op plus, and we take a look at what that does, it takes in an int of a function, right, creates a function that takes as an parameter, right, a function that maps from an int to an int list, and then maps that all to an int. That's basically what it's doing. Finally, if we give it the, if we build this up one more step, fold_r op plus 0, right, it gives us just the int list mapped to an int. Okay, and then finally, if we save that to a value, right, so we store it in a value, add up equals fold_r op plus 0. What that gives us is the capability to take any list and just add up its contents, right? So essentially, it's performing the aggregation function summation. So we say add up 1, 2, 3, 4, 5, and then of course we get 15, which looks great. It's very slick, very easy way of doing this. Now on the other hand, we have the fold_l, right, which is used to combine all the elements of a list. Same results as fold_r in some cases. Now note, we have this will get into what the difference between fold_r and fold_l actually is. So examples where we get the same value are if we use fold_l op plus, and then we put 0, 1, 2, 3, 4, right? And then we run fold_l op times on 1, 1, 2, 3, 4. We get the same result. Sorry. I always forget the space. 1, 1, 2, 3, 4. Okay, we get 24, right? Well, so the fold_l function works slightly differently. Alright, so it adds up all the elements of a list X. We could write fold_l, to add up all the elements we write as we did before, fold_l op plus 0x, right? It takes a function f, a starting value c, and a list x, which is equivalent to x1 through xn, and computes the function f called on x sub n, comma, the function of x sub n minus 1, all the way down through the function of x called on the function called on x sub 2, comma, the function of x sub 1, comma c, right? So the interesting thing is the opposite direction in which we went before, right? Fold_r works from the head of the list down to the tail. The fold_l starts at the tail and works down to the beginning, right? So it folds left, right? So if we were to think about this, fold_l is folding this down leftwise, whereas fold_r is folding it rightwise. Okay, does that make sense? So that's how you have to kind of think about how these functions are applying. It's applying the function from the right, from the left towards the right if it's fold_r, and from the left, from the right towards the left in fold_l. Just having to understand the semantics, because they can actually, depending on the type of operation you're applying, cause all sorts of issues to occur. So as I said, fold_l starts at the left, fold_r starts at the right. Difference does not matter when the function is associative and commutative. Right? We say starts at because the first thing that's actually done in fold_l is the leftmost item, or the rightmost item. But it starts at the left. The left item is 1, right? So it starts there. Whereas the it starts at the leftmost the leftmost item. So it'll be 1 plus 0 in FoldL, right, the leftmost item is the one that's solved first, whereas the rightmost item in FoldR. So by looking at the parentheses applied during the operation, just to keep that in mind. So FoldL starts at left, FoldR starts at right. Difference does not matter what function is associative and commutative, right? That's what plus and multiplication are. But for other operations, for example, string concatenation, subtraction, division, these things are not commutative and associative. So you'll have to watch out for that. So for example, if we were to perform the fold R op concatenation, right, on ABC, DEF, and GHI, and then apply it to fold L op concatenation, we get completely different answers, right? Before we got, with fold R, we got ABC, DEF, GHI. This time we will get GHI, DEF, ABC. Right? Not quite what we wanted. Well, assuming that's not what we want. So just bear that in mind when you are operating in when you're operating the ML language. All right, that's it for this lecture. The next one, the next programming lecture will be ML4, and then we won't have anything until after spring break when we start Java 1. All right, have a great one, and I'll see you in class.